So I put 41 and 42 together on the homework because they're both referring to that same figure. On number 41, what is the force on the charge located at 8 centimeters in part A of that figure, given that Q? And now on the question, we have positive Q, that's 1 microcoulomb. We have negative 2Q, that's negative 2 microcoulombs, and positive Q again, and I could change that value, obviously. So the Coulomb force equals K Q1 Q2 over R squared. Since we're figuring this out in relationship to the charge that is at 8 centimeters, we have positive Q here at position 3 centimeters, and we have negative 2Q located at 8 centimeters, and then positive Q again at 11 centimeters. What we're going to figure out is the electrostatic force between those two guys, and then the electrostatic force between those two guys, and then do the vector sum. The vector sum, it's all in the same x-axis, so we don't have to do three-dimensional vector summing. Is that a word? So we just have to do it in one dimension. So the force, and life becomes easier if you're doing big things, lots of things with subscripts. The force between the particle at 3 centimeters and 8 centimeters is going to be K, 9 times 10 to the 9th, times Q1, that's 1 times 10 to the negative 6 coulombs, times Q2, negative 2 times 10 to the negative 6 coulombs, divided by R squared, the radius, the distance between the two, that's 5 centimeters, 5 times 10 to the negative 2nd meters squared. K is 9 times 10 to the 9th. I plug in those numbers and I get a force of 7.2 newtons. This charge was positive, this charge was negative, so that's an attractive force. For our 8 centimeter charge, that is a force directed in the negative x-axis. Each of those charges feels an attractive force. The force that positive Q feels is in the positive x-axis. The force that the 8 centimeter position one feels is in the negative x-axis due to this charge. We have another charge, force between 8 and 11. These two are closer together, and the force is in the distance is in the denominator and it's squared. So if it's a smaller number squared, we wind up with a bigger force. So 9 times 10 to the 9th Newton meter squared per Coulomb squared times negative 2 times 10 to the negative 6 coulombs times positive 1 times 10 to the negative 6 coulombs. Now they're only separated by 3 centimeters, 3 times 10 to the negative 2nd meters squared. I run those numbers and I get positive 20 newtons. Again, this charge is attracted to this one, so it's in the positive x-axis. This charge is attracted to that one, so that's in the negative. But our perspective is all here with that charge that was positioned at 8 centimeters. So for that charge, this one was in the negative x-axis. This one was in the positive x-axis. Sorry about the microphone here. And so when we add those two together, accounting for sign, we get a net force of positive 12.8 newtons, and that is directed to the right on the number line, or positive number line, or due east, however we want to say that. Whew. All right, so that's number 41. Oh no. 42. So now we're on the next number line down with a whole bunch of charges there. If we wanted to measure the electric field at position 1 centimeter, there's something there. There's a big negative charge there. In the EM field lab that you did or will do, you will discover that if you try to measure the electric field right on top of a negative charge, it's negative infinity. The distance to the charge is 0, and the force equals K Q1 Q2 over R squared. If R is 0, if you have 0 in the denominator, the answer is negative infinity, which our math majors will hate. So just a really big negative number. Part B, if we let them move around and equilibrate, they're going to cancel each other out just like they would in any atom or molecule. If there's a positive charge for every negative charge, then that's neutral. If we do that, that's part C. Part B. Part B, we want to find the electric field at 11 centimeters. So now it's kind of like we did with number 41, adding them up. Now we're going to do it 4 times. When we do that and account for sign, we get 2.12 times 10 to the 5th newtons per coulomb. So we're figuring out the electric field exerted by each charge, accounting for sign. And then finally, part C, we have a net charge in the mix. We have 4 positive charges and 3 negative charges. So we have positive 1 net charge at the end when they move around. I hope that helps.